So, continuing the lecture, we were at the point where we were considering the one sample z-test. It's actually not often used in psychology because, as you'll see, it compares the mean score of one group against the known population mean. And this can only be performed when we know the population mean and the population standard deviation. So often in psychology we will know what the population mean might be under a null hypothesis, but we very rarely know the population standard deviation, and so we can't often perform this test, but it's very useful because it's the basis of a lot of other tests such as the Ttest. So we have to teach you this in basic statistics. So to perform a one sample z-test, what you do is you calculate how many standard errors of the mean above or below the population mean your sample mean is. So we can express that as a formula, as a z-score. It's your actual mean, your sample mean, minus the population mean, which is represented always by mu, expressed in standard errors of the mean, which, if you remember, is the standard error of the mean is the standard deviation of the sampling distribution of the mean. And remember, we know from the central limit theorem that the standard error of the mean is the population standard deviation divided by the square root of the sample size. So we've performed this previously, but we're just going to flesh it out with a specific example. Say we had a population of individuals in IQ, which is a population mean of 100, and by the design of IQ tests we know the population standard deviation should be 15, and our sample had a sample mean of 106, and let's suppose, given the sample size of 36, the standard error of the mean we saw before was 2.5. If we divide 6 by 2.5, we get a z-score of 2.4, and when we look that up, we get a p of 0.008, which is significant. So this asks us the question, answers the question precisely that we asked earlier of what's the probability of getting a sample mean in a sample of 36 from the normal distribution of IQ, which is exactly equal to 6 points above or below the mean. That would be the two-tailed version. So just to show you this, schematically on a normal distribution, this is the sampling distribution of the mean based on samples of n equals 25. Here the population mean is 250 in this example, and the standard deviation of the sampling distribution of the mean, which is the standard error of the mean, is 10. So we want to know if we had a sample mean, x bar, the bar over the top is a way of denoting a mean, of 272, we would know the z-score was 22, which is, for this point, it's 22 points above the population mean, divided by the standard error of the mean, 10, gives you 2.2, a z of plus 2.2. Similarly, so this area, this is this point here, this little blue circle. So we're interested in whether this lies outside the standard confidence limits or the rejection, in the rejection region here or here. So to calculate these, the critical value of z at the 5% two-tailed level is plus or minus 2, or more precisely 1.96, drawn in here. So 95% of a normal distribution lies between a standard normal distribution lies between a z-score of minus 1.96 and a z-score of plus 1.96. This here, this white region, is the region of retention, the region where we cannot reject and have to retain the null hypothesis. The rejection regions in blue are the areas where we reject the null hypothesis and declare a statistically significant effect in this case. And we see that our particular z-score is in the rejection region two-tailed, because it is above, with a score of 2.2, is above plus 1.96. One sample z-tests, and this slide runs through some examples. Let's suppose we've taken a group of 16 people and measured their IQ and calculated the mean IQ of that group as 103. We want to ask the question that we've talked about before of whether this mean is significantly different from that we'd expect based on the population with parameters that we've previously specified. No, because we can do the following calculation. The standard error of the mean, remember, is the standard deviation of the population, which is 15 for IQ from a normal population by design, and it's divided by the square root of the sample size, so 16, and square rooted is 4, so the standard error of the mean is 15 over 4 or 3.75. So we can calculate a Z statistic based on that, which is the difference between the means, 103 minus 100, divided by the standard error of the mean, 3.75, which conveniently gives us a score of Z of 0.8, because 3 divided by 3.75 is 0.8. And we can then look up in various ways what the probability is, a two-tailed probability, because we're asking whether it's significantly different, not in any particular direction, from the mean of 100 for the population. We do a two-tailed test, and when we look up the value of Z equals 0.8, we can see that the probability is greater than 0.4, and so clearly this is a non-significant result. So now we are now considering some dice throws. Now we have a sample of 25 dice throws, and we want to know, is this sample likely to have come from a fair die or dice? And the mean score is 3.85 for those 25 throws. Now we know the expected mean for a population, or for a fair of throws from a fair dice, is 3.5. We worked it out earlier, and it turns out, using a formula that mathematicians have worked out, that the standard deviation you'd expect for a dice is roughly 1.7 for throws in the population. So we can do the same calculation using the same approach, and this time we conclude that it is from a fair dice, because the sample of mean of 3.85 is not significantly different from the population mean that we'd expect. We can do this calculation, so yes, the answer is yes, it is from a fair die. The standard error of the mean is 1.7 divided by the square root of 25 throws, and the standard deviation was 17. If we put that into the Z calculation, the difference between our sample mean and the population mean is 0.35, which is divided by the standard error of the mean, 0.34, and we end up with a Z of approximately 1, which is not significant two-tailed. The P is in excess of 0.3. So just to make the last calculation of the p-value more concrete, we've drawn a standard normal distribution with mean 0 and standard deviation 1. So our z-score was +1, as we calculated in the previous slide, and so this means the p-value we're looking for is the probability of finding a value of z either greater than +1, so in this area, or less than -1 in this area here. So we know from the properties of a standard normal distribution that actually 84.13% of the distribution lies between above one standard deviation. Sorry, that should have been below one standard deviation. So that means that roughly 16% lies above. Similarly, there'll be another 16% below -1 standard deviation below the mean. So if we add these two areas together, we get something in excess of 30%, which is why we concluded that there was no significant difference, and so we could not reject the idea that this was a fair dice because we use a p-value of 0.05 or smaller in social science. So this illustrates or moves us on nicely to another major topic in hypothesis testing, which is the nature of statistical errors when you do hypothesis testing. And psychologists and other social scientists distinguish two types, type 1 and type 2. So type 1 errors are false positives. These are when you have said there is a significant effect and there isn't one, when the null hypothesis is actually true, but you reject it. And the rate of type 1 error that we adopt conventionally is the critical significance level, or the probability value alpha. So typically it's 0.05. So what we're doing by setting that probability level of 0.05 is we're prepared to accept a 5% type 1 error rate as a maximum. In other words, we say we reject the idea, in that last example, that these sample of throws were from a fair dice because, well, not in the data we gave, but in another example the p-value might have been below 0.05. That means we're prepared to risk that level of error, 5% or less, in claiming that this was, in that example, the dice were not fair. The throws were not from a fair dice. The flip side are so-called type 2 errors. These are misses, if you like. This is where there is a real effect. The null hypothesis isn't true, it's false. We should ideally declare the test statistically significant, but we don't. And they occur with a probability of beta. Now, actually, it's rarely known amongst undergraduate psychologists, and probably not known amongst many people who've done PhDs and even some members of staff in academic departments. But actually, there's a general consensus that we don't want beta to be higher than 20%. Ideally, we should design our experiment so that if there is an effect there, we have at least an 80% chance of discovering it, declaring it significant in our experiment, i.e. we're prepared to accept a maximum of about a 20% chance of a type 2 error. So here we draw them out here. This is the true state of the world with respect to the null hypothesis H0. So it's either true or false, and our decision is we either reject it, we find a statistically significant effect in most cases, it works that way around, or we don't reject H0. We can't find enough evidence to reject the null hypothesis. The test is in most situations is non-significant. So a type 1 error is this cell of this table, and the probability is alpha. That it should be an alpha, it's not showing up properly. And then of course the correct decision is when, in this case when H0 is true, is we say no, we can't reject H0. So that has a probability of 1 minus alpha. Similarly, our type 2 error rate is when actually there is something going on and H0 is false, but we don't have enough statistical evidence to reject H0. We make a type 2 error with probability beta, and then the complement of that is when we correctly detect something's going on and reject H0, so it's another correct decision, and here the probability is 1 minus beta, and in statistics that is known as statistical power. So statistical power is defined, following on from what we've just said, as the probability of correctly rejecting a false null hypothesis H0. In other words, it's the probability of detecting an effect that is really there in the data and declaring it significant. And more formally, we can say power is 1 minus beta, where beta equals the probability of a type 2 error, or the type 2 error rate. So, just to look at the dice example again in terms of power, H0, the null hypothesis, is that it is a fair dice. So it turns out that the sampling distribution of mean scores from fair dice have an approximately normal distribution. even with sample sizes as small as n equals 25. It's 25 throws, as we saw earlier. So we can draw that out here, and the mean score under the null hypothesis of a fair dice is 3.5. And it turns out that the standard deviation can be calculated approximately 0.34, 0.35. Let's work with 0.35 for calculations. So the standard error of the mean is 0.35. If we have 1.96, or let's again make it simple by having two standard errors of the mean above or below the mean. So 2 times 0.35 would be 0.7. If we add 0.7 above, we get 4.2, and we take off the population mean, 3.5. If we take off 0.7, we get 2.8. So the rejection region is above, if our sample mean is above 4.2 or below 2.8. So if you suspect someone is using an unfair dice, get them to throw 25 throws, add up the score, and if the score lies outside the region of 2.8 to 4.2, you can conclude that it's not a fair dice. That's the rejection region to reject H0 with a two-tailed 5% significance test. So we can draw that graphically, and we've drawn the null hypothesis. So now let's draw a line, our decision line, at 4.2. We could do it equally well at 2.8, but let's just work here. Then against the null hypothesis, this decision line here cuts off an upper tail of the null hypothesis with probability alpha, or alpha over 2 for a two-tailed test, because there's another alpha over 2 down here. So 2.5%, 2.5%. But let's suppose this dice, the one, let's suppose under some alternative hypothesis, H1, the dice is rigged, has slightly more probability of getting high scores, and its actual true mean of the sampling distribution of the mean for that false dice would have a mean around 4. I've drawn it around 4. So let's suppose we apply our null hypothesis test and the appropriate decision for the 5% level of a 4.2 boundary. Then if the alternative hypothesis were true, H1 were true, then we would, so this would be all the occasions that might occur, all the samples that might occur, it's the sampling distribution. So then we would make a type 2 error this proportion of the time, i.e. every time we got a score below 4.2. Let's make it one-tailed to keep it simple. So this would be beta, and this would be our power, which is in this case less than 50%. So only this white region, the H1 distribution to the right of this line, would we declare the dice to be not fair. It would be significantly different from what we expect under the null hypothesis. So this illustrates that in this situation we have a relatively low power to detect the effect of a dice which has just a 0.5 higher than the mean score expected under the alternative hypothesis. So we can see that as we move this decision line up and down, we alter the alpha rate, but we also alter the beta rate in an opposite way. If we make alpha accept a larger alpha level, we reduce beta and we increase our power. Power is the opposite part of this distribution from beta, which is shaded with the horizontal lines. So we can move on from the one sample ztest to the one sample Ttest. The one sample ztest, as we've already seen, is when we know both the population mean and the standard deviation. The population mean and standard deviation used for the null hypothesis. So often in psychology, as I've already said, we don't know the population standard deviation, although we might well know the population mean under the null hypothesis. But as we don't know it, and it's represented with a Greek sigma, lowercase, we can estimate it from S, which is the population, the sample standard deviation. Notice sample statistics are usually denoted by their equivalent in standard alphabet to the Greek letter. So sample standard deviation is S. But unfortunately, S, as we measure it in a sample of observations, is a skewed but not a biased estimator of the population sample signal standard deviation sigma that we're trying to estimate, and Howell describes this very clearly. In fact, S is often smaller than it's too small, smaller than the true value sigma that we're trying to estimate. So if we did a one sample z-test using S as our estimate of sigma, then it would be inaccurate. So we turn to an alternative statistical distribution, not the normal distribution that applies to the z-test, but the so-called Tdistribution, which applies to the t-test. So the construction of the one sample t-test is exactly like the one sample z-test we've already done, but it just uses a different distribution, the Tdistribution. So we perform our one sample t-test in the same way. We take the sample mean from the population mean under the null hypothesis, and we have an estimate of the standard error of the mean, and it's an estimate because it's based on S rather than sigma. So we calculate the t ratio rather than a z score or a t-test value, t ratio, this way using our estimated standard error of the mean, and we correct for the bias that this, or the error that this introduces, by using an alternative distribution, the Tdistribution. And so we look up on a different table, or we use a different output computed distribution value. The Tdistribution is also referred to students' Tdistribution, and that's because it's the statistician who originated it, William Seeley Gossett, shown here, who worked for the Guinness Company in Ireland, was not allowed to publish work under his own name, or he was worried about doing it, so he published under the anonymous name student, and that's why it's called the student's Tdistribution. A paper in the early 1900s. So, a Tdistribution, what's it like? For a sample size n, the Tdistribution has a parameter of degrees of freedom, and there are n-1 if the sample size is n. So the t-test also has a certain number of degrees of freedom. And that's because we've used one fixed parameter measured from the sample, S, and we therefore, to do that, we fix the sample mean when computing the t value. So a normal distribution, in fact, that we're all familiar with, is a Tdistribution with an infinite number of degrees of freedom. So as the sample gets smaller, as the degrees of freedom move towards 0, the Tdistribution gets so-called more platykurtic. That means it has broader tails than the corresponding normal distribution. Now I use a mnemonic to help me remember this, because it's I think a Greek word, platykurtic. This is to do with the tails, and this means broad. There's an animal called a duck-billed platypus, which is a marsupial found in Australia, and it has characteristic feature, has a very flat, broad tail. So platykurtic distributions have broad tails. This is a graph showing a normal distribution and a Tdistribution with 20 degrees of freedom. You see it has broader tails, and that with a very small sample with degrees of freedom of 5 has even broader tails. I think we show that again in rather nicer graphics here. So rule of thumb, if you've got 30 or more in your sample, the T and the Z distributions start to look very alike. So we use the Tdistribution in carrying out t-tests, such as the one sample t-test, in much the same way as the z-test and the normal curve. We look at the areas, the rejection region here and here. This is for a 5% two-tailed test, and the retention region between here and here. But because the tails are a little flatter and broader, it's not minus 1.96 and plus 1.96. When the degrees of freedom are 16, i.e. for sample sizes in the one-tailed test of 17, we would have critical values of minus 2.12 and plus 2.12. So not very different, but we're allowing for that small amount of inaccuracy because we're using an estimate of the population standard deviation. So here's a table that you can use, one-tailed or two-tailed, with small degrees of freedom for very small samples. These are the proportions in two tails of the T-distribution. Let's take an example. 5%. You see, even with the samples as small as 7 for a one-tailed t-test, degree of freedom of 6, the critical value is only just around 2.5, 2.4, 2.45. Not that far away from the 1.96 of the normal distribution. So the basics for a t-test. Makes assumptions about the population based on sample data. Put simply, it's the observed difference between the means. Ask the question, is the observed difference in the means real? The means being the sample mean and the population mean under the null hypothesis. And it says, is that observed difference real, or is caused by some real effect, or is it just simply the result of sampling error, normal variability that you get when you take a sample, different samples from a normal population, from a population. And it's a ratio because it looks at observed differences, the mean difference divided by some index of variability, the standard error of the mean, estimated from the sample standard deviation. And so the bigger the t-test score, the more likely it is that the observed mean differences are real and not due to chance. So looks at the different types of t-test. We've talked about one sample t-test. This is used to compare a sample against a single reference point, a population mean under the null hypothesis, mu, the expected score under the null hypothesis, and it's very similar to the one sample ztest, as I've said. And you use the one sample ztest in those rare occasions when you don't have to estimate the population standard deviation, you know it. You use a t-test most commonly in psychology because we don't often know the population standard deviation. Then there are other types of t-tests. The independent samples t-test, comparing two different samples of observations with one another, between groups it's also sometimes known as, and the repeated measures t-test, where there's one sample but there are two measures of the same variable. That's why they're repeated measures, and we're concerned with the difference score D between the two scores for every participant, every case, and that's what we're concerned with rather than the raw scores. This is sometimes known as a paired t-test, and these will be covered in later lectures. So we just quickly whiz through a one sample t-test example. Imagine we had an ESP experiment, extrasensory perception experiment, parapsychology experiment, where we know on this test, maybe it's a guessing test with 80 items with a 50% chance. So we know that a score of 40 would be expected just by chance if ESP did not exist. That's the null hypothesis. It doesn't exist. And so we want to know, what sort of score would we need to find statistically significant evidence for ESP on this test. So say we measure a sample of 10 self-proclaimed psychics who do the test, and they obtain a mean score for the sample of 10 of 43.2, so above the chance value, but we were asking, is it statistically significantly above the chance value, the null hypothesis value, and their sample standard deviation S is 5. So we could do the calculation in a minute, but a common mistake when estimating if this represents above chance performance would be to use the sample standard deviation. So we do our t-test just calculating that using that value. But in fact, one should use the sample based estimate of the standard error of the mean. So remember, you have to divide the sample standard deviation by the square root of the sample size. So square root of root 10 is 3 and a bit. If you divide that by 5 divided by that gives 1.58. That's our measure of variability in the denominator, the bottom part of the t ratio, the fraction used to calculate t. So we put it here, and the difference 43.2, take away 40 is 3.2, divided by that 2.03, and that's a t with a df of 9 because it's n minus 1. This was the sample size, n of 10, n minus 1 is 9. So we look up the value of the t for df equals 9 for a value of 2.03, and we find what the probability value is. And we find on a one-tailed test, because we were the psychics were all claiming they could do above the chance score, would be p equals 0.04. So this would be a rare experiment, assuming it was well controlled and well conducted, where there was significant evidence for ESP on this test.